Everyone's here, so let's get started. So let's do problem 2. So I'm going to do the first example, I'm going to do the first problem, and then I'll give you the second problem, okay? So after this, we'll do an interesting demonstration. Okay, so calculate the density of CO2 at 295 Kelvin, so that's the temperature of my room, and 1 atmosphere, okay? So CO2. First step is to okay, so we want to know the density. So the density is weight divided by volume, okay? And weight equals the number of moles times the molecular weight, okay? So our first step should be to rearrange the ideal gas law into something that looks like this. N over V equals P over RT, okay? Now, let's just calculate this. So 1 atmosphere divided 0.08206 times 295. Okay. So, okay. Okay. Now, can someone tell me what the molecular weight of CO2 is? So look at your periodic table. So here's carbon, here's oxygen. So all we need to do is to take this, so 0.0413 moles per liter times 44 grams per mole equals 0.82 grams per liter. So this is the density of CO2. Great. Okay, so now we have the density of CO2. Now I want you to do something a little bit harder. I want you to calculate the density of air. Density of air. So this can be, so you can break this up into steps, which I've outlined for you. So we need to calculate the density of air at 295 Kelvin and 1 atmosphere. So by moles, air is 78% nitrogen, 21% oxygen, and 1% argon. So the mole fractions are 0.78, 0.21, and 0.01. So I want you to, so I've put this together nicely, okay? So calculate the density of air. And if you want, you could ignore argon, okay? You could ignore argon. So I'll give you 10 minutes to do this. I'll do this one in red pen. Okay. So we are given the temperature, so 295 Kelvin, and 1 atmosphere. Okay. So now we just need to, so now let's do this step by step. Let's do nitrogen first. So let's find nitrogen first, and then we can just add all of them together, okay? Okay. So now, can someone tell me what the partial pressure of nitrogen is? Remember, all you need to do is multiply the mole fraction by the total pressure. So equals X. So can someone tell me what it is? So nitrogen is 78% of the total, and the total is 1 atmosphere. So it's just 0.78 atmospheres, right? So equals 0.78 over RT equals, oh, let me cross that, 0.7 divided by 0.026. Okay, so 0.0319. Okay. Now, can someone tell me what the molecular weight of N2 is? The molecular weight. So looking at a periodic table, yep, 28, okay? So 28. So multiplying these two together, we get, so 0.893 grams per liter. So now we can just repeat the same for all of this, okay? So then we should get, can someone tell me what this equals? Oh, that should be 295, but it shouldn't, it doesn't matter, it's fine. Okay, so this equals 0.00868. So now, can someone tell me what the molecular weight of O2 is? Great, 32. So we get 0.278 grams per liter. And I'll just do argon for you. So 0.01 over R295 times 40 equals 0.01. 0.016 grams per liter. Okay, and now we just need to sum all of these together. So the sum of these is 0.0319 plus 0.02. Sorry, it should be this. This plus this plus that. So 0.893 plus 0.278 plus 0.016. So the total is 1.187 grams per liter. Okay? Well, what I want you to notice is that CO2 is denser than air. Okay? CO2 is denser than air. So I'm going to do a demonstration based on this fact. So CO2 is, okay, so now I need a source of, I need to make some CO2. So now, how do we make CO2? So the reaction is NaHCO3 plus CH3COOH goes to H2O plus CO2 plus, okay? Can someone tell me what this, does anyone know what these are? You can, here's a hint, you can find them in your house probably. Okay, so this is baking soda, and this is vinegar or acetic acid. Okay, has anyone done a baking soda volcano? A baking soda volcano? Has anyone ever done that in like elementary school or something like that? Yeah. So we're going to use that reaction to make some CO2, and then we can do some stuff with that CO2. So let me change the camera. Okay. So you might need to turn the volume up a bit since I'm not speaking into the microphone right now. So can everyone still hear me? Okay, great. So what I'm gonna do is first I'm gonna light this candle. There we go. So you have a lit candle. Let me turn down the lights. Okay, so now I need to make some CO2. So I have here with me, I have a beaker here. So what I'm gonna do, I'm gonna take some, where did I put my chemicals? Here it is. So I'm gonna take some baking soda. Just gonna put it in here. Whoa. The candle just went out for some reason. So I'm gonna have to relight it. I think there might be some water in there or something that's preventing it from staying alight. I think I might need to use the blowtorch. So let me, okay. So this is a bit more dangerous, but I'll be careful. Please don't go out. Well, it just went out. That's annoying. So I have here some vinegar. So I'm just gonna slowly add it to the baking soda. You can see it immediately start bubbling. Okay. Might be a bit too much, but it's fine. I'm gonna go ahead and cover this. Oops. Okay. So now what I'm gonna do is I'm gonna try to pour the gas over the candle. So go ahead, you can make your predictions as to what you think is gonna happen. It's not bubbling. Okay, so we now have some CO2 gas in a container, and I'm gonna pour it onto the flame. So without pouring any of the liquid into the flame, I managed to to put out the fire just by pouring gas. So let's do that. I think we can do that again. There might be enough gas. There might be enough CO2 left to do it again. Try it again. not enough. Okay, that's fine. But I think you get the point that some gases are more dense than others, and we can calculate these densities, okay? So let's go back to this PowerPoint. Okay. So I just want to briefly talk about Graham's law for a second. So basically, this Graham's law is based on the idea. So the velocity of the gas. So remember, all of these gas particles are moving around randomly. So we want to be able to know what the average speed of these gas particles is. And we call this the root mean square speed. And this is equal to 3 times r times t divided by the molecular weight in kilograms to the 1/2 power, okay? So you don't need to worry about this too much, but the point is that diffusion rate is inversely proportional to the square root of the molar mass. So diffusion is like, you know how if you spray perfume in one area of a room, you'll be able to smell it in another area on the other side of the room. So this is because of diffusion. The particles in the perfume are traveling onto the other side of the room. So here, one example of demonstration of this is we have a tube, and at both ends, we put a piece of cotton soaked with ammonia and soaked with HCl. So HCl has a high molar mass, but ammonia has a lower molar mass. So the ammonia will travel faster and it will diffuse faster. And when these two gases react, we get a white solid, ammonium chloride. So you can see this ring of white salt form somewhere in the middle of the tube. And it turns out that the distance to the ammonia side is longer than the distance to the HCl side because the ammonia travels more than the HCl because the ammonia moves faster. Okay? And now I want to talk about Henry's law real quick. So Henry's law is the idea that the solubility of a gas is proportional to the pressure of the gas, directly proportional to the gas. So how does this matter in our daily lives? Well, not necessarily daily lives, but if you ever go scuba diving, you have to rise to the surface slowly, because otherwise you might suffer what's called the bends. So when you go deeper in the water, the pressure increases because you're further underwater. So there's more weight of water pressing down on you. So the pressure increases when you go down. So that means more nitrogen gas dissolves into your bloodstream, okay? So more nitrogen gas dissolves in the blood. So you're deep underwater and your blood is filled with nitrogen. What happens when you rise to the surface very quickly? Now, all of this nitrogen suddenly doesn't want to be in the bloodstream. So now your blood is filled with these nitrogen gas bubbles, and this can be lethal, actually. So just to kind of show this, I have a syringe. So let me see. Okay, camera. Walgreens syringe. So I'm going to fill it with a little bit of water. Some water. Okay, and let's get rid of the gas bubble on the top. Okay, so as you can see, this syringe is completely filled with water, and there's no gas bubbles. So there's no gas in here, it's just water. Now, what happens when I pull on this syringe? What's gonna happen to the pressure? So what do you think will happen to the pressure if I pull on the syringe? Remember Boyle's law, right? So as the volume increases, the pressure will decrease. So let's see what happens. So as you can see, we have all of these bubbles coming out of the water. And these are all bubbles of dissolved gases. So under atmospheric pressure, all of the gases will remain in the water. But once I pull on the syringe, I've created a low pressure area. So now all of the gas wants to come out, and so you can see the bubbles form. I don't know. It doesn't seem like it's very visible on camera, but yeah. Okay. So maybe you can see that a bit better. There's a bunch of bubbles there. Okay. So, and I did want to say one more thing about gas solubility. So it turns out that as you increase the temperature, gases become less soluble. So if you've ever like turned on the hot water faucet, you might see that the water looks cloudy because the gas, so originally the water will be cold, so there's a lot of gas dissolved in it, but once you increase the temperature using your water heater, all of the gas starts to come out of solution, and now you have these bubbles in your water which cause the cloudy water. Okay? Let's see. Do I have another slide? Why won't it go? Okay, so I think that's the last slide. And we have a little bit of time left. We have about 10 minutes left. So do you want to talk about a different topic, or should we do some more practice problems?